Welcome to Data Engineering with Subadip. In this exciting tutorial, we will dive deep into mastering streaming joins and state management, unlocking the power of real-time data processing with Flink and Spark. Get ready to enhance your data engineering skills. Today, we'll cover the core concepts of stateful streaming, dive into streaming joins and their challenges, differentiate between event time and processing time, understand watermarks and how to handle late events, explore checkpointing for fault tolerance, and finally, look at practical examples like sessionization and fraud detection. What is stateful streaming? In essence, it's about remembering past events to process current ones. Operations like aggregations, joins, and pattern detection require storing intermediate data or context across multiple events or time windows. It's like your system remembering what just happened to understand what's happening now. Why is state management crucial? It's essential for real-time aggregations, like counting unique users, performing streaming joins by merging continuous data, detecting complex patterns, sessionizing user activities, and ensuring fault tolerance by allowing recovery after failures. Without it, these advanced real-time operations would be impossible. Streaming joins present a unique challenge. Unlike batch joins, where all data is available, streaming joins involve continuously arriving data streams. This means we must manage time-based windows, handle out-of-order events, and maintain state for potentially long durations. Imagine joining user clicks with ad impressions to calculate real-time conversion rates. That's a streaming join in action. A critical distinction in streaming is between event time and processing time. Event time is when an event actually occurred at its source, offering the most accurate view for business logic, but it's prone to out-of-order data. Processing time, conversely, is when the streaming engine processes the event. While simpler, it's less accurate for historical analysis as it depends on data arrival order. Watermarks are essential for taming event time processing. Since events can arrive out of order or be delayed, watermarks act as special timestamp messages. They tell the system that all events with an event time less than or equal to the watermark's timestamp are considered to have arrived. This allows windows to close and accurate results to be emitted, ensuring correctness in our real-time calculations. Late events are those that arrive after their corresponding watermark has passed. To handle these, we can configure a grace period, allowing a window to remain open for a defined duration after the watermark. Flink offers side outputs to redirect late events for separate processing. Some systems can also emit updated results if a late event changes a previously computed outcome. Your choice depends on your application's needs for accuracy versus latency. Checkpointing is vital for fault tolerance and stateful streaming. It's the mechanism that periodically saves the entire state of your streaming application to persistent storage. If a failure occurs, the application can restart from the latest successful checkpoint, ensuring exactly once processing guarantees and preventing data loss or reprocessing from scratch. This is fundamental for robust real-time systems. Both Apache Flink and Spark streaming offer robust state management. Flink provides powerful state backends like RocksDB, ensures exactly once guarantees with distributed snapshots, and has first-class support for event time watermarks. Spark structured streaming offers a high-level API, uses checkpoints for fault tolerance, and integrates watermarks for event time windows, along with stateful operators like map groups with state. Let's look at a practical example. Sessionization using Spark structured streaming. Here, we group user events into sessions based on a 10-minute inactivity period. We define a watermark on the event time and use a window function with a grace period. This code reads user events from Kafka, extracts the user ID and event time, then groups these events to define user sessions. The results are then printed to the console. For fraud detection using Flink, we can identify unusual transaction patterns. For instance, detecting 3 transactions over $1,000 from different locations within a 5-minute window. This conceptual example uses Flink's value state to keep a count of high-value transactions per user. We key the stream by user ID, apply our custom aggregator, and then print the results, triggering a fraud alert if a threshold is met. For more complex patterns, Flink SEP would be used. To excel in stateful streaming, choose the correct time characteristic, event time for accuracy, or processing time for simplicity. Tune your watermarks to balance latency and correctness for late events. Select the appropriate state backend, like RocksDB for large state, or memory for small and fast state. Always enable checkpointing for fault tolerance. Monitor your state size to avoid performance impacts, and optimize joins efficiently, using bounded state or time window joins. Thank you for watching. We hope this deep dive into streaming joins and state management with Flink and Spark helps you build more robust and efficient real-time data pipelines. Don't forget to like, share, and subscribe for more data engineering content from Data Engineering with Subadip.